I hope you had a chance to watch the demonstration video with projectile motion. The problem we're going to solve today is a projectile motion problem in one dimension in the y direction when the ball is shot straight up and comes straight back down. I'll read the question. A ball is launched vertically with an initial velocity of 14 meters per second. What is the velocity at the maximum height? What is the maximum height? And what is the velocity when the ball returns to the launch height? Neglect air resistance. Well, what we have here are two columns of pictures, and they show the relative amounts of the total energy that's either kinetic or gravitational potential energy. So when the ball is first launched, and when we deal with these problems, wherever the ball starts is defined as 0. So you might be starting from a little cannon above the ground. You can call that 0, as long as you understand that 0 on the way back down is also even with the mouth of the launcher. Okay, so in state A, we have all kinetic energy. And as the ball continues to rise, it gains a little bit of potential energy, and that's in state B. And then it's getting quite high. It's slowing down, thanks to the acceleration of gravity, and less of it, the energy is kinetic, and more of it is potential, until finally, in state D, it's all been converted to potential energy, and the ball has stopped. This is how we define the maximum height. So when we look for the velocity at the maximum height, we can know that that's defined as 0 velocity in the y direction. So let's write that down. We know V sub A, and that's the initial velocity in state A, equals 14 meters per second. And we know V sub D, which is the maximum height velocity, that equals 0 meters per second. Okay, I'm going to double check and highlight the initial velocity, and that V sub A at state A, that's the initial velocity. And then in state D, we have the velocity at the maximum height. And that's this one right here. It's 0. I've put an X there showing that there's no length to that arrow, so there's no velocity. We can write here V sub D. Now we need to answer what is the maximum height. Well, we're going to need to use energy conservation, and we're going to need to write down all of the knowns and identify our unknown, because we'll be using the equation for energy conservation. So what we would also need to know are the heights at the two states in state A and state D. The height in state A, we know that there's no potential energy in state A, and that means that it's at height equals 0. So there we have it. We have 0 meters for the height at state A. And our unknown is the height at state D, or the maximum height. So I'm going to use energy conservation to solve this. And we know that we start with the kinetic energy plus the gravitational potential energy in the first state, or the initial state. And then that's equal to the sum of the kinetic plus the potential energy in the final state, or a second state. It doesn't matter which two states you're going from, as long as one is initial and one is final. So in our case, we're actually going to call A our initial state and D our final state. Okay, there we have it. We can see once again, the m's cancel, so this answer is independent of mass. And substituting in the 0 values, which are the velocity of state D and the height in state A, we see that this term is 0 and this term is 0. So in the end, we're only looking at changing the velocity from state A into the height at state D. Solving this, we get H sub D equals V sub A squared over 2G. Substituting in, we can find that h sub d equals 14 squared divided by 2 times 9.8. And not forgetting the units, we have meters per second squared divided by meters per second squared. It's a bit complicated. That equals 196 divided by 19.6. And this simplifies to meters squared divided by, second squared divided by second squared meters. The seconds cancel, and one of the meters cancels, leaving us with a singular meter. 196 divided by 19.6 equals 10. And we're left with meters, which is great since height is measured in meters. The final thing that they'd like to know in this problem is what is the velocity when the ball reaches its initial height. That means that we need to get all the way back down to state G, right? And really, you can break these problems up into two halves. And we can put D back up here, call that D, then E, F, and G, right? Since the ball stopped at state D, really we just, from state D onward, are in a state of standard free fall. The ball starts from zero velocity and is accelerated down. Well, we've solved this problem already. We know that the velocity right before it hits the ground of a ball that starts at 10 meters high is 14 meters per second. But we also know this by looking at the energy conservation equation that goes between state A and state G. Remember, you can go between any two states. And all of the kinetic energy is transferred to kinetic energy from state A to state G. So we know that the velocity in state G equals 14 meters per second. What energy conservation doesn't tell us is the direction. And we need to look at the illustrations here to figure that out. Remember that our initial velocity, we didn't write it down. The initial velocity was actually in the positive y direction. It was up in the opposite direction to gravity. And our velocity in state G is in the negative y direction.